Hello, welcome back. The title of this lesson is Relative Motion in Two Dimensions. So here we're effectively doing an introduction to the theory of relativity, but the theory of relativity begins with some foundational stuff. You first talk about one reference frame in motion with respect to another one and how to convert essentially coordinate systems. Everybody moving around has their own coordinate system centered on their self. In classical physics, we say that it's the spatial coordinates. Originally, we talk about relative motion in one dimension, and we only care about one direction, the x or the y direction. In this lesson, we're going to consider everything to move in the xy plane. However, this is very extensible to three dimensions, x, y, and z. Well, when I walk around, I have a local coordinate system on me. And everything I measure, as far as things moving, is all relative to what I see in my reference frame. And if someone else is moving relative to me in some arbitrary direction, well then they're going to have their own measurements of what they see. And I can convert the coordinates that they see in their reference frame to what I see in mine by some simple calculations that we learn here. And we've already learned them for one dimension. But just keep in mind that everything we really learn here, we know is not totally correct. When we get into the theory of relativity, which has withstood the test of time on actual experiments, when we get into high speeds, these equations that we're using to add and subtract velocities are not totally correct. It's very important to learn them, though, because we have to know where we're coming from at low speeds in everyday experience, so that when we get up near the speed of light, we understand the deviations from the normal everyday stuff that we see. So we don't have to worry about relativity in everyday life. Even something fast like a rocket or a spacecraft orbiting Earth, relativistic effects are not that pronounced. But when you get up near the speed of light, they're absolutely essential and critical because you get massive differences in your calculations versus reality. So how do we go from one dimension in the last lesson to two dimensions here? All right, I'll give you a spoiler alert. In one dimension, it's basically just numbers, because you only have one dimension really. But in 2 and 3 dimensions, they turn into vectors. That's the basic idea. Vectors are the object that allows us to work very easily in 3 dimensions. And another spoiler alert, when you get into relativity, you have something called a 4 vector, which also includes time. And we also learn in relativity theory down the line that just like these spatial dimensions can be changed depending on the reference frame you're in, well, it turns out that time also can be measured differently depending on the reference frame that you're in. And so space and time become kind of a thing called space-time. They're just different aspects of the same overarching canvas that we all live in. Time seems to be this thing that ticks independently of everything, but actually that's not true. The ticking of time actually is dependent on your state of motion, also dependent on whatever gravitational field you're in. It changes the ticking of time. So there's just kind of an aside there, but that's where we're going. So in one dimension, we illustrated, this is from before, and I'm going to extend it to 3 dimensions of space here, or in 2 dimensions of space mostly here, but very easily extensible to 3 dimensions. In one dimension, we only had the x direction. This here, I labeled it y, but really it's a dummy variable. There's nothing really here. It's only measuring stuff in the x direction. And we said we had a stationary frame, somebody standing on the ground at rest, and we had somebody moving in a car at low velocity v. So all this stuff is very accurate at low speeds. You get high speed near the speed of light, these equations don't work so well. And that's what Mr. Einstein taught us. So anyway, frame B is the moving frame at some velocity v. And then we said there's some event out there called P, and that event could be anything. It could be you're observing a rock flying through the air, a bird, a cloud. It could be anything going on way out here. And frame A, the stationary person, will be able to observe this event and measure some position and velocity of this thing. But frame B, moving, also will be able to measure some position and velocity of this thing. So the velocity as measured by frame B of event P by frame B is called xpb, right? And then the difference in the frames, they're displaced one relative to the other. Pretend the car maybe drove by just a little bit. The position of frame B is called xba. That's frame B as measured by frame A. So the subscripts are very important. They tell you what you're measuring, and they tell you who's measuring it. It's extremely important because all this stuff changes depending on who's measuring it. So in order to calculate the position of the event with respect to the stationary frame, what we do is we take the event as measured by the moving frame, and then we add to it the velocity of the moving frame with respect to A. So it's kind of like if you think about one of those conveyor belts that you see at airports, and you can get on there and you can walk in the direction of the conveyor belt and get going really, really fast. So that's basically a similar situation here. If you have a stationary observer looking at this whole event here, they're going to see the conveyor belt moving with some velocity. Then they're also going to see the person walking along the conveyor belt at some velocity. And from the outside observer looking, it's going to be the sum of those velocities. It'll be how fast the conveyor is moving with respect to the ground, plus how fast the person is walking with respect to the conveyor belt. You add those two velocities together, and then that's going to be what I measure of the event with respect to frame A, the rest frame. So those are the positions. And notice I also drew this here. When you write the subscripts like this, the interior index B here is kind of like it kind of goes away. This is kind of like when you multiply by 50 and you divide by 50, well, you don't really have to multiply and then turn around and divide. You just know that multiplication and division undo each other. So in reference frames, when the variable is the same on the inside like this, it kind of goes away. And so PA is what's left over. All right. Now, we said we can take the derivative of this and turn these positions into velocities. So this becomes the velocity PA, this becomes the velocity PB, and this becomes the velocity BA. And so this is what I was saying. The velocity of some event as measured by the stationary observer is equal to the velocity of the event as measured by the moving observer, plus how fast the moving observer is moving relative to the ground, to A. And we can take another derivative and show that these, because this is called an inertial frame, where the moving frame is at a constant velocity. If we take another derivative, then the derivative of this, since it's constant, will disappear. And so this turns into an acceleration, this turns into an acceleration. What this equation is telling you is that the equation for the acceleration of some event happening out there will be measured to be the same in both frames. Even though the velocities are all different, the rate of change of the velocities, as measured by different inertial frames, will be the same. Remember, an inertial frame is just a frame moving at a constant velocity relative to some other frame. All right, so that was all review to get us where we need to be. How do we go from working in one dimension, only the x direction, to 2 dimensions, the xy plane, or to 3 dimensions, the xyz three-dimensional space we live in? Well, I'm not going to draw another picture because I have to draw 3-dimensional coordinates and it gets ugly. But basically, these equations turn into vector equations. So remember this, x, PA, PB, and BA. So those turn into position vectors. R, PA, is equal to R, PB, plus R, BA, right? Literally, this position as measured from the origin of the coordinate system is only in the x direction. This turns into a vector because vectors, the position vector bookkeeps the position of some point in space. Now, I'm writing it in 2-dimensional space because that's as far as we're going to go, but it's the same math for 3 dimensions. You just have the x, y, z coordinate. Now, these are vectors. These are not just numbers you add together like before. These are actual vector quantities. So this, for instance, this BA, this position of frame B with respect to A, this is how the two frames are positioned relative to one another. But in general, you might have the frames not sliding in one direction. You might have the frame moving in 2 dimensions with respect to one another. Or in 3-dimensional space, you might have one frame like off in 3 dimensions somewhere far away, not in any particular plane from the original observer. So this vector stuff takes care of all of it because it's all 3-dimensional. This vector of BA is the displacement or the difference in space between the two frames of interest in any kind of 3-dimensional orientation or 2-dimensional orientation. All right? And these are the positions of B with respect to how frame B, of the event P with respect to B and so on. But they're all 3-dimensional. So whereas before it was like a 1-dimensional thing, the event was only along the x-axis, kind of like in the same direction. Now the event can be anywhere. I can be looking up at the event. I can be looking down at the event in the plane of the xy plane. Of course, easily extensible to 3 dimensions, which is just one more dimension to keep track of. So if that is the position vectors, what do you think the velocity vectors will look like? Well, you guessed it. It's going to be PA, PB, BA. And what this is saying is that the velocity of some event is measured in frame A, the stationary frame, is equal to the velocity of the event is measured by the moving frame plus how the moving frame is moving. But whereas not in just the same direction, in a vector plane, so they can be moving anywhere in the xy plane, and these vectors will take care of calculating the new velocity vector in the stationary plane. And so when you take the derivative again, you get the acceleration is equal to the acceleration, just like we said for the x-axis, because this is a constant. The velocity of the B frame with respect to the A frame is a constant number. By definition, it is an inertial frame, so it's a constant velocity between the frames. So you take the derivative, you get 0. So the acceleration is measured in both frames are identical, just like it is in the x-axis. Basically, all these equations just become vector equations. So now you kind of see why we learn vectors. Why do we have this thing called a vector? Because you can learn things in one dimension, in one direction. And then you can just turn those equations into vector equations, and suddenly you have the whole universe in front of you, and you can do things in 3 dimensions. And then later on the time dimension in 4 dimensions. Okay, so there's no more diagrams, no more drawings. These are the equations. What I'd like to do is solve the first problem. It's a little bit of a weird problem, but very practical problem. And once upon a time, a long time ago, for fun, you know, I got a pilot's license and an instrument rating. And so flying airplanes, you have to be cognizant of the wind. Always. When you're trying to land an airplane, if the wind is coming straight at you, which is what you want, by the way, you want the wind coming straight at you over the wings, it's much, much easier than if you're flying and you have wind coming straight at the side. And if you have a wind coming behind you, that's really bad because you can tip your plane over if you're going too slow. So a direct crosswind is what we call it whenever the wind is blowing at you from the side. And as you might imagine, if I'm flying an airplane toward you and the wind is blowing me, well then I'm not going to be going directly toward you. I'm going to be drifting this way. I am still going to be coming toward you, but I'm going to be also moving sideways. And so that is an important thing for landing and taking off an airplane. So this is all about that. An airplane experiences a crosswind of 25 miles an hour, actually 25 kilometers per hour. And it's perpendicular to the runway where the airplane must land. It's kind of what I just described. The plane's speed relative to the air is 80 kilometers per hour in the direction that the nose of the plane's nose points. Find the angle between the direction where the plane's nose points and the runway's direction that will make the plane's velocity relative to the ground parallel to the runway. This is a bunch of words for what I was trying to describe to you. If I'm flying directly toward you and I have a stiff wind coming straight from my side, because you can't move the runway, so sometimes the wind does come from the side. If I do nothing at all and point everything directly toward you, what's going to happen is I'm going to move toward you, but also sideways. And I'm not going to land on that runway very nicely because I'm going to be going sideways and not in the same direction of the runway. How do I counteract that? Well, if toward me and you is the direction of the runway, what I need to do is turn my airplane into the wind, turn the nose into the wind. The wind is coming from this way, so I turn my nose this way, crabbing into the wind a little bit. So you can think of my velocity vector of the airplane as trying to go not straight down the runway. However, because the wind is blowing at me, then the sideways components kind of cancel out. And so even though the nose is pointed this way, I am moving directly toward you. And if we're a very stiff crosswind, you might have to turn that nose very, very far in order to go down the runway. Now, you might say, how are you going to land an airplane if your wheels aren't even lined up with the runway? Well, what you do is when you get very, very close to the ground, you can almost always turn the airplane back toward the direction of the runway, because the way the wind works, the way the fluid works, the fluid flow in the atmosphere, wind is a fluid, air is a fluid, the velocity of the wind speed is always much, much higher way up in the air, and it goes close to 0 near the ground. Even on the windiest day that you feel, it's much, much windier up in the sky. So what you do is you crab into the wind, and you get down very close to the runway, and then maybe one wing length to the ground. Then you turn it back this way and you land the plane, cut the power, and you land the plane. And if for some reason the wind is gusting so bad that you cannot turn it parallel and land it, then you gotta give it full power, and you have to go around and try again. Maybe go to a different airport to find better weather, because you have to be able to put the wheels in the direction of the runway. All right, so that's a bunch of geeking out over airplanes. Let's talk about how to do this. So now you can see the vector nature of it, right? Because even though it's three-dimensional space, the airplane we're considering to be rotating in 2 dimensions. And also, this problem is a little weird because it says determine the angle between the blah, 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 you know, the nose of the plane and the direction of the runway. But we haven't done anything with angles in this. We've just done these relative velocity problems. So, but you got to remember that angles are implicit in vectors. And so the direction and the angle is just what the vector is. So we have to draw a picture, and you might draw several pictures, actually. So let's begin that process by drawing a couple of different pictures. So here's the x direction, here's the y direction. This is the top-down view, a top-down view looking at the airplane, right? And you might think of this being the runway. So I'm flying and I really want to land on this runway like this. Unfortunately, I have a very stiff crosswind. You can think of the airplane being kind of in the center right here. I'm not going to be able to draw an airplane here, but you get the idea. I never said I was an artist. Okay, that's an airplane. Yahoo. You can think of it as a bird, whatever you want to think of it. All right, well anyway, this airplane is experiencing some kind of crosswind. It's coming from this direction. So you can draw the arrow impinging on the plane like this. That's fine. Or you can move the arrow over here so that you can envision it pulling it this way. They're both correct. So what I'll do is I'll just draw this way. And this is the velocity of the air, not airplane, of the air with respect to the ground is 25 kilometers per hour. See, this is stuff that the problem isn't giving you. It's not telling you about wind. But when someone tells you the wind speed, it's always relative to the ground. So this is the velocity of the air. That's what wind is, velocity of the air with respect to the ground. That's why I have, instead of 2 subscripts that are hard to remember what they are, we just relabel it and say, okay, this is the velocity of the air, comma, with respect to the ground. Those are my indices. All right, now what we're saying is that in order to land on the runway, the airplane is not going to be able to go straight with the nose pointed down the runway. We're going to have to crab you know, in the direction of the wind. Remember, the wind is coming this way. So what we'll do is we'll say that the velocity vector of this thing is really off in this direction somewhere. Okay? And so this is the velocity of the plane, that's p, with respect to the air, and that's equal to 80 kilometers per hour. Now notice that as soon as I crab the airplane in like this, in a different direction other than the direction I want to go, it means that there's always an angle here. And actually, this angle is what I'm trying to find. So the question can be rephrased a different way. Basically, it can be phrased like this. Airplane's flying to the runway. You have a stiff crosswind from the right. And your airspeed, that's what you use in airplanes, it's the velocity relative to the air. Airspeed is given by this. And you have to turn the airplane at some angle to counteract the stiff wind blowing from this way. How many degrees do you need to turn your airplane so that your ground speed will be going straight down the runway? Remember, the nose of the plane might still be cocked off at an angle, but the actual plane itself is still going in the direction you want, directly down the y-axis here, which is the runway. Now, this drawing is pretty good. I mean, it's okay, but I think we can clean up the drawing a lot. All right, so let's draw this again. I mean, you got to start somewhere. You can't always get the best drawing immediately. So what you have is a vector. This air is a vector. It's going, it's a crosswind, and so even though it didn't tell me north, south, east, west, I'm assuming this is north and this is east, west. And so this thing I'm basically saying is going to be a direct east-west thing. This is some angle from north, if you consider that to be north like this. All right? So what you have is a vector situation. The airplane is moving off, let me use the same colors. The airplane is doing this. And so I'm going to relabel this here, VP air, right? And it's 80 kilometers per hour, like this. And the wind is right here. But remember, when we add vectors, because that's ultimately what we're going to do. Remember, this is all about adding vectors. The velocities are we're going to write these down in a second, but we're going to end up adding the vectors, and you'll understand why in just a second. But when you add vectors, even graphically, you can move this around freely, but what you want to do is you want to move it head to tail. So these are tail to tail right now, but to add them graphically, you want to move it up here so it's head to tail, right? Which is what you want right here. And so I'm doing it in red, and I'm going to move it over here like this. And so this is the air with respect to the ground, 25 kilometers per hour, like this. So you have a vector situation. Adding vectors, there should be some angle, which I'm going to find, such that if I take this vector and add it to the velocity of the crosswind, the resultant vector, which is the only one I don't know. I know the purple one and I know this one. The resultant vector is straight up and down, right? The ground track is straight along the direction of the runway. That's what you want, because this, I could draw a little runway if you want to, but whatever. That's a runway right there. All right, so what would the equation be? What would be the addition of these vectors, right? Well, the velocity of the plane with respect to the ground, which is what I want, is got to be equal to, vectorially, to the velocity of the plane with respect to the air, plus the velocity of the air with respect to the ground. Notice these are vectors now, which means when I say these are vectors, I remember I didn't understand early on, well, what does that mean? Okay, well, if they're not vectors, they're just numbers. It's like 5 plus 2 minus 3, numbers, right? But if they're vectors, they have directions and they have angles. So to add them, you don't just add numbers, you have to add them either graphically or component by component to get the answer as a vector, right? That's what it means to add the vectors together. So we moved it up here so we can visualize it in terms of a triangle here. What this is saying is the velocity of the plane, the vector velocity of the plane across the ground with respect to the ground, is equal to the velocity of the plane with respect to the air, this vector, plus the velocity of the air with respect to the ground, this one. So that means this black vector is equal to this vector plus this vector. That's what this is saying, okay? And notice that air is the interior index here. And so just like I told you, you have two B's right there, and I had it written on the other one. When you're adding vectors like that and you're using relative indices like that, the interior index, if you have the same one, they drop away. So what you get is PG, the plane with respect to the ground. So we know that the equation is correct. So what you're trying to do is but notice the problem doesn't say, tell me the resultant vector. What it actually tells us is, tell me the angle. But we know that by adding these together, we want a straight up and down resultant like this. And so by a straight up and down resultant, we know that this angle here from north is going to be the angle that we want. Okay? And so what we want to do is calculate this angle. How do we figure out what that is? Well, the sine of that angle is going to be the opposite over the hypotenuse. So the opposite side is this, the hypotenuse is this. Notice I know both of those angles. I know both of those numbers, or vectors, I should say. So the sine of that angle is going to be the opposite side, air, G, divided by VP, air. And notice I'm dropping the vectors because whenever I'm doing the sines, I'm only looking at the length of the triangle. See, you have to write the vectors down to know that you can form it into a triangle. And then because that's what vector addition is, and then once you have the triangle written down, the sine of the angle is just the length of the opposite side. So it's no longer a vector, it's just the length of it, the scalar, divided by the length of the hypotenuse of this side. Okay? So that means that the sine of the angle is going to be equal to 25 kilometers per hour divided by 80 kilometers per hour, and the units cancel, so I can just leave 25 divided by 80. So theta is going to be equal to the inverse sine of 25 over 80. So whenever you take a 25 divided by 80 and take the inverse sine, you get 18.2 degrees. And then you have to ask yourself, does this pass the smell test? Is this in the correct quadrant, right? You look at your drawing and you're getting a small positive angle less than 45 degrees, which matches what we have here. You're just doing a sanity check. This one should be longer, this one should be shorter, so the angle is going to be less than 45 degrees based on just trying to draw it roughly to scale, and that's exactly what I get. You could also rotate this around and make sure it's in the correct quadrant, however you want to do it. But you want to always make sure when you take the inverse trigonometric function that the angle, it makes sense from a quadrant point of view. So you might say, well, in this problem, we got the angle correct. 18 degrees is what you have to crab in this case, to continue moving down the runway along the runway. But you might say, where's the vector addition? You opened this thing up and you said, well, here you have to use vector addition to get the answers. But this problem didn't seem to really have any vector addition. And I'm going to tell you that it is implied in the way you solve the problem. When we took the step of going from here to here, we made it into a vector addition problem. you have this airplane, it has a vector acting on it this way and a vector acting on it this way, which is basically the airspeed. And when we rearrange it like this, and then with the air stopping right here to produce a resultant along the vertical direction, at that point is when we did the vector addition. It was just kind of like a secondary thing. We have to assume that they add like vectors, and we have to assume that the resultant lies directly on the y-axis so that this angle is the one I'm trying to find, right? That's where the vector addition comes from. Some problems are more explicit. They'll say, what is the vector resultant, or what is the velocity vector in this reference frame, and you'll have to spit that out. In this case, we just ask for the angle. But implicit in drawing a vector triangle like that, you're doing vector addition. This is the runway, and basically implied in the problem, it says determine the angle between the direction where the plane's nose points and the runway's direction that will make the plane's velocity relative to the ground parallel to the runway. Implicit in that is you want the airplane to land on the runway, so it has to be going straight up and down. Implicit in that means you want the resultant of those two vectors when you add them to be directly on the y-axis, which is the direction of the runway. Therefore, that angle is going to be the crab angle from the nose of the plane and the direction of the runway. So it's all wrapped up in all those words there. So, tricky problem, but mostly it's talking about airplanes, which I love to do. You know, it's been a while, but it's fun, right? So, please, do this yourself. Draw your own diagram. Yours might be a little different than mine. That's okay. And then when you do that, follow me on. We have one more problem with relative motion in 2 dimensions. Learn anything at mathandscience.com.